Hello students, today I'm going to run you through some of the reactions involving aqueous cations listed in your data booklets. Okay, so that will be on section 9A, where you are given the qualitative analysis of some of the cations in your syllabus. Hopefully they will help you in your practical revision. We are also looking at the reaction of some of the anions listed over here, as well as to test for some of the common gases. Okay, then towards the end, you will get to see the colors of the halogens in organic solvents such as hexane, as well as in aqueous solution. Okay, so we'll first be looking at three colorless cations. So what are they? Yeah, so first we have aluminum 3+ over here. Okay, then next we have magnesium 2+, and then this is followed by zinc 2+. Okay, so I'm going to introduce 1 cm depth into each of the test tube. For each test tube, I'm going to test with sodium hydroxide, and then the other test tube, I'm going to test it with aqueous ammonia. So first, I'm going to do it with Al3+. Okay, so I'm just going to add in 1 cm depth. Okay, test tubes. Okay, and then I'm going to add in aqueous sodium hydroxide over here. Okay, so I'm going to add in dropwise. Okay, so please observe the change. Okay, you do expect white PBT to appear. Okay, so I think the appearance of the white PBT shouldn't come as a surprise. And then when I add in sodium hydroxide slowly in excess, you notice that the white PBT starts to clear. Some of it starts to dissolve to give you a colorless solution. Okay, so that shouldn't be a surprise. Okay, so yeah, so this is what you observe. Colorless solution obtained. Okay, so this is one of the most common chemistry you are being introduced to in H2 chemistry, as well as I do believe that you have seen it before in secondary school. Okay, then I'm going to just do a slight extension, which you have done them before in several other labs earlier on. I'm just going to add in dilute hydrochloric acid dropwise, and I want you to observe what happened to the colorless solution. Okay, at this point in time, you might just want to pause the video and make a prediction what you observe, and then you see whether it matches what you observe. Okay, just going to add in dropwise, so please observe carefully. Okay, do you see the appearance of precipitates? Okay, you can see that there's a rim of PBT at the surface. Just need to be very clear not to swirl it. Okay. Not sure if it's obvious to you, there's a rim of PBT right at the surface. Okay, and then when I swirl it, it will dissolve. Okay, it will start to dissolve when we experience the volume of the whole test tubes or of the whole solutions. Okay, so I'm just going to repeat this dropwise. Okay. Okay, you can see the PBT appearing again. Okay, and then when I swirl it, it dissolves. Okay, and then I swirl it, it will start to dissolve. Okay, of course, more PBT appears right now. Okay, so right now, the PBT will not dissolve. Okay, why is that the case? Because I added just enough hydrochloric acid so that the excess OH minus has all been reacted. So essentially what I have now is just enough OH minus to precipitate out aluminum 3+ as aluminum hydroxide. Okay, then when I add more, I think you do expect that the aluminum hydroxide dissolve to give you a colorless solution, because aluminum hydroxide and hydrochloric acid will undergo acid-base neutralization reaction. Okay, so when if I touch the test tube, of course you can't feel it over video, but it's actually warm to the touch. Okay, so now it dissolves in excess to give me a colorless solution. Okay, right. I'm going to explain to you the chemistry. You have seen it in the chemical periodicity video, but over here you have seen it a live demonstration, so I hope it helps. Okay, you also have heard some of the explanation in transition metal chemistry, but nonetheless, I'm going to explain it on the board. Okay, now the first thing we need to be clear about is when we add in OH minus, okay, what are we looking at? So we are actually looking at the precipitation reaction between aluminium 3 plus and OH minus. And this actually leads to the production of AlOH3 solids. So this is the precipitate being formed, the white precipitate you observe. That's nothing very different from what you have learned in secondary school, because in secondary school, this is how you write a balance equation. This is how you write an equation for the formation of an insoluble salt or insoluble hydroxide. Okay, but not to forget, in JC, you learn something about solubility products. So for solubility products, we know that when more and more sodium aluminum hydroxide is being produced, it will then maintain a small amount of Al3 plus and OH minus by virtue of its KSP. Okay, so we have equation 1 here and equation 2 here. So equation 1 represents the precipitation reaction of aluminum hydroxide. Reaction 2 represents the small amount of Al3 plus and OH minus being maintained by virtue of its KSP. So we define KSP by equilibrium 2. But what happens when excess OH minus is being added? Okay, so when excess OH minus is being added, right, we are being accompanied by equilibrium 3. Okay, so when excess OH minus is being added, there is a favorable equilibrium being established due to the formation of the highly soluble aluminate complex AlOH4, okay, minus. So this complex is highly soluble, so we get equilibrium 3 being formed. Then why is it that aluminum hydroxide eventually dissolves in excess when excess OH minus is being added? Because in excess OH minus, okay, the excess OH minus will react with the small amount of Al3 plus being maintained by the KSP of aluminum hydroxide, that is equilibrium 2, and then in the process favors equilibrium 3. So when equilibrium, or rather reaction 3 or equilibrium 3 will take place in the forward direction. And when reaction 3 is being favored, right, aluminum 3 plus is being removed from equilibrium 2, and therefore the equilibrium 2 is being disturbed. And according to Le Chatelier's principle, because equilibrium 2 is being disturbed, position of equilibrium will then shift to the right for 2. And what you observe over there is that your white PPT dissolved in excess hydroxide, which leads to the formation of aluminate complex. And that's why in the very beginning, when you observe your solution, or when you make your observation, it's actually a colorless solution. Okay, and then what happens when I add in hydrochloric acid? Okay, so when I add hydrochloric acid, all hell breaks loose because I am disturbing 2 and 3 to some extent. Okay, remember when OH minus, when H plus hydrochloric acid is being added, right? OH minus is being reacted away via an acid-base neutralization reaction. Yeah. So when OH minus is being added, when H plus is being added, now I react with the OH minus. So position of equilibrium of 3 now shift to the left. Okay, and the system recognizes that the amount of OH minus is no longer in excess. Yeah, so and because the amount of OH minus is no longer in excess, and in the solution I have quite a large amount. I mean, it's not that large, but some amount of Al3 plus. Then equilibrium 2 will then occur. So you can call it the backward reaction of equilibrium 2, or you can say that 1 will then operate, which leads to the formation of aluminum hydroxide as the white PBT. Okay, then eventually when I add in excess hydrochloric acid or H plus, the aluminum hydroxide will react with the H plus via acid-base neutralization reaction, and then eventually it will lead to the formation of Al3 plus as well as H2O. And then whether you choose to call Al3 plus as a naked cation or the hexyl aqua aluminum 3 complex is really up to you, because this discussion is not very crucial in our explanation, at least for at the H2 level. Okay, so I hope this explanation gives you a glimpse on what exactly is happening when I add in OH minus to the Al3 plus solution. Okay, so next I'm going to move on and add in aqueous ammonia to the Al3 plus solution, which I've added earlier on. Okay, and if you look at your QA sheets, you will know that I'm just going to observe white PPT insoluble in excess. So let's see whether this is what we observed. Okay, so I'm just going to add in dropwise. Okay, yeah, so you're going to observe white PPT. Okay, so I think it's quite obvious. PPT forming, I swirl the solution a little bit. A little bit gelatinous than earlier on. Okay, but if I add in a little bit more, it's not going to dissolve very well. Okay, so this is not soluble. Okay, so this is a swirling technique which you need to practice. Okay, so I'm just going to add a little bit more. It's not going to dissolve. Okay, so for Al3 plus, when you add aqueous ammonia, white PPT appears insoluble in excess. Okay, I also hope you understand why you will observe the white precipitate. The white precipitate is actually aluminum hydroxide as well, and that is due to the partial ionization of ammonia in water, which produces OH minus, and one will operate. Okay, and when one operates, the ionization of ammonia continues until most of the ammonia ionizes to give us ammonium as well as OH minus. Okay, yeah, so that's why you observe. And when you want to when you want to see whether the white PPT can dissolve in excess, you want to check whether the element 3 plus can form a complex with aqueous ammonia. So that is whether the hexyl aqua aluminum complex, whether the water ligand can be replaced by ammonia. But in our case here, it seems that it's not being replaced. Okay, because the white PPT remains. Okay, yeah. So next, we are going to look at another colorless solution. Okay, so that would be magnesium 2 plus over here. So this magnesium 2 plus, I'm going to do the same thing, add in 1 cm depth. Okay, and then add in another 1 cm depth. Okay, and then what I'm going to do is same. Okay, I'm going to add in aqueous sodium hydroxide. So please watch what is likely to take place. Okay, so clockwise, can you see the white PPT? Relatively gelatinous PPT being formed. I add in excess, but it remains insoluble. Okay, yep. Okay, so so for Mg2 plus, when sodium hydroxide is being added, white PPT form insoluble in excess. Okay, I'm going to do the same to aqueous ammonia. So this aqueous ammonia. Okay, so I'm going to add in clockwise. Okay, so you observe white PPT being formed as well. Insoluble in excess. Okay, so same ideas we are looking at. Okay, so make sure that when you swirl, you don't swirl too hard until all the solution gets kicked out of the test tube. Okay, so just make sure you swirl gently. Okay, so next I'm going to look at zinc 2. This is zinc 2. Okay, again 1 cm depth very quickly. Okay, 1 cm depth. Okay. Okay, so same idea. I'm going to add in aqueous ammonia. Sorry, not aqueous ammonia. I'll add in sodium hydroxide first. Okay. So dropwise. Okay, so you observe the formation of the PPT as well. Okay, so the PPT is slowly forming. Okay. Okay, so I'm going to slow down a little bit. And then when I add in a little bit more, you notice that the PPT starts to clear up a little bit. So here we observe white PPT soluble in excess sodium hydroxide. Okay. Okay, I'm just going to add rim so that the PPT at the walls of the test tube gets dissolved. Okay, you get a color solution. Okay, so why is that the case? Similar story. Okay, I'm not going to explain it again because basically now what you're going to do is just going to replace the element 3 plus with zinc 2 plus. And then the complex form is zincates. Okay, of course for zinc, it will be zinc hydroxide, which is ZNOH2, not ALOH3. Okay, yeah, so this is the resultant color solution. And of course, in your QA sheets, white PPT soluble in excess to give us a colorless solution. Okay, so next, zinc 2, I'm going to add in aqueous ammonia. Okay, so let's observe what's going to happen. Okay, so dropwise again. Okay, so you can observe PPT at the rim. Okay, it's a little bit gelatinous. Okay, I'm going to swirl slowly. Okay, yep. Okay, very, very slowly. Just going to do that. Okay, you notice that the PPT starts to clear out a little bit. Now it settles at the bottom. I'm just going to swirl it to allow it to experience the volume of the solution in the test tube. You can see that it begins to clear out bit by bit. Okay, so I'm just going to swirl. Sometimes it takes a bit of time and patience. Okay, it does not occur immediately, but do give it a bit of time, a bit of swirling. Okay, so I'm going to add a bit more. Okay, you can see that it's very clear that now the PPT clears up. Okay, so white PPT dissolve in excess to give us a colorless solution. Okay, in case you are wondering what is this colorless solution, it's actually a complex. Okay, tetraamine zinc complex. Okay, so I'm going to illustrate this on the boards. So again, it's the same idea. Okay, so first I'm going to erase this. I'm just going to replace this with the N2+. Okay, almost everything else stays the same. This is the N2, ZN2, okay, and then ZN. Okay, and then this is ZNOH2, ZN2+, 2OH minus. Okay, then of course the third equation will be different. Okay, for third equation, we are writing another form of zinc 2+ in the form of the complex. Okay, so that will be ZnH2O 6 2+ plus 4 ammonia. Okay, equilibrates to give us this plus 6 H2O. Okay, yeah, so this is very important, okay, for us to understand. Okay, so I guess 1 and 2 we are familiar. Then what happens when we add excess aqueous ammonia? Okay, so when we add excess aqueous ammonia, right? Ammonia is now the ligand. Okay, so it will undergo ligand exchange with the water ligand in the zinc 2 complex. And then in the process, it will lead to the formation of this new complex known as tetraamine zinc 2 complex, which is soluble in water. Yeah. And in our case here, the position of equilibrium will be pushed all the way to the right, because this complex is more stable as compared to the hexyl aqueous zinc 2 complex. Okay, the first question you might have in your mind is, why is it that at the beginning I do not observe the complex being formed? Okay, now if you do not swirl the test tube, there will be some complex. Okay, later on I'm going to illustrate using the copper 2 example. Okay, but what exactly is happening? I'm going to erase the equation number. There's one equation which I did not write earlier on. This is 4, 3, 2. Okay. So the first equilibrium that is taking place and we need to be able to understand and take note of it is the formation of OH minus from the ionization of ammonia. Okay, so first of all, we know from acid-base equilibrium that ammonia is a weak base. So it's being a weak base, it will ionize partially to give us a little bit of ammonium and a little bit of OH minus. Okay, however, right, in the presence of zinc 2+, the little bit of OH minus will then react with the zinc 2 to form zinc hydroxide, which is a soluble, it's an insoluble salt or insoluble hydroxide, so you precipitate out. So the precipitation of zinc hydroxide will push the position of equilibrium of 1 to the right, leading to more aqueous ammonia ionizing, and therefore there will not be any molecular ammonia accumulating in the solution, because any molecular ammonia accumulating in the solution can potentially lead to the formation of this complex. Yeah, so in the very beginning, there is no molecular ammonia accumulating in the solution because of the fact that I have a lot of zinc 2 plus, which reacted with the OH minus to form zinc hydroxide precipitate, and this result in the position of equilibrium of 1 to shift to the right. Yeah, so when that happens, there is no way ammonia can remain as ammonia or molecular ammonia. You will have to ionize. Okay. However, right towards the end of the precipitation, I do not have a lot. I don't have a lot of zinc 2 anymore, because now the amount of zinc 2 in the solution is nearly maintained by the very small KSP value of zinc hydroxide. Yeah. So when I add in aqueous ammonia, the small amount of zinc 2 will definitely not be able to form much precipitate with OH minus. Yeah, so this actually leads to the accumulation of ammonia, and then now another reaction operates, which is ligand exchange. Yeah, so ligand exchange will then take place with the hexa-aqua zinc 2 complex, and in the process, it displaces the water ligand, which leads to the formation of the soluble complex, which you observe as the excess solution. Which you observe as the colorless solution. Okay, that is the colorless complex which you observe towards the end. Okay, which I believe it's over here. Okay, so this is the colorless complex. Now, the question which most of us have at the back of our mind is what happens when we add hydrochloric acid, like what we did earlier on. Okay, so maybe at the back of your mind, you might want to predict. For this, I think it will be quite obvious what happens when we add excess hydrochloric acid to the zincate complex. You expect similar things to happen as that of, similar to aluminate complex. Okay, so when you're curious, you want to know why, just verify yourself. Okay, hydrochloric acid to make sure I don't add the wrong thing. Okay, so you see, I'm going to observe the same thing. Precipitation being formed, if I don't swirl, it will just stay. If I swirl, you will just dissolve. We can understand why. Okay, so we're going to add in just enough to react away all the OH minus, so that now the precipitate will be permanently formed like this. Okay, so this is not surprising. Essentially, what we are looking at is zinc hydroxide, largely zinc hydroxide now. Okay, any excess acid I add, right, will react away all the zinc hydroxide to give me zinc 2. Okay, so we can verify it over here. Okay, so if you touch the wall of the test tube, it's warm because of the acid-base neutralization reaction. Okay, I'll probably need a glass rod, but I think swirling will just work. Okay, it's quite warm now. Okay, so I think this is not surprising, not very inspiring, because we saw that from aluminate. Okay, now shall we try for the tetraamine zinc 2 complex? Let's try. Okay, we'll see what we can understand, whether we do get the PPT. Okay, so let's see. Okay, so let's observe very slowly. Can you observe the little tiny little bit of PPT being formed right below? Okay, so maybe it's not so clear cut. Let us try again. Okay, it's usually formed at the bottom. Okay, just a little bit. You can see that PPT is forming. Okay, notice that I did not swirl because I allowed the solution to slowly flow through. I don't want to agitate it so that you can feel the whole volume of the test tube. Okay, but if I swirl it, I'm sure it will dissolve. Okay, just like what happened when we added hydrochloric acid to the solution containing zincate. Okay, see, you get the same kind of observation. Okay, so we'll do it slowly again. Okay, you can see that the PPT is slowly forming. You can see that when I add hydrochloric acid, it just flow through, right? And then you can see the PPT being formed right at the side if we don't disturb it. Of course, when we disturb it, it will dissolve. Okay, yep. If you add too fast, you will not be able to observe much things. Okay, like this. Okay, So if I just add fast and I swirl, yeah, everything will dissolve. All the PPT will dissolve. Okay, so this is something which you expect to observe. Okay, so right now, yeah, there won't be any more apparent changes. Yeah, because most of the zinc hydroxide has already reacted to give us zinc 2, and the solution should be sufficiently acidic. Okay, yeah, so we are done with the 3 colorless solution. I hope you find that useful. So that's aluminum 3+, zinc 2+, and what's the remaining one? Mg2+. Okay, then next we'll move on to something colored. Okay, so we are probably looking at iron 2 and copper 2. Okay, yeah, so now I have iron 2 with me. So it's a pale green solution. Okay, so again, I'm going to add 1 cm depth. It's same idea. 4 test tubes. Okay. Yep. So I'm going to go through the same process. Sodium hydroxide as well as aqueous ammonia. Okay. So sodium hydroxide, I'm going to add dropwise. Please observe. I'm going to get more colors appearing. So this is the green PPT. In the past, we described this as dirty green because you can see that it looks a little bit like the algae growing around the drain. So this is the dirty green PPT we are often talking about. Okay. Okay, I'm just going to show it a little bit more. Okay. Yeah. So this is the dirty green precipitate we often observe when we add in sodium hydroxide to iron 2. Okay, so after a while, you will observe that the precipitate near the surface of the test tube will get oxidized to reddish-brown iron 3. Okay, so we'll just observe that. So this is the one which I've added sodium hydroxide. Okay, now I'm going to add using aqueous ammonia. So I want you to take note as well. So this is aqueous ammonia. Okay. Yep. So again, you do observe the dirty green PPT. Do take note that this is not gray-green. Some of you think that it's actually chromium 3. Yeah, it's a little bit different, huh? Yeah. Okay. So I'm just going to add in excess to see whether it is soluble. Okay. Okay, so this is aqueous ammonia. This is sodium hydroxide. Okay. You start to notice that some of the precipitate at the side of the wall already starts to, at the wall of the test tube already starts to gets oxidized to reddish-brown PBT. So this is the sodium hydroxide one, okay, in case you forgot. Okay, I can add in a little bit more sodium hydroxide, okay, so that just to make sure that the volume is similar. Okay. Yeah, this is the aqueous ammonia one. You observe that the PBT near the side of the container gets oxidized quite quickly. Okay. So I'm just going to swirl both. Okay. We are going to revisit them later. Okay, I'm just going to place it over here. Okay, remember from the review of practical 21, I mentioned that once you put it over in the test tube rack, the PPT will start to settle down. Yeah, that is where you know that we are looking at PPT and not complex. Okay, yeah. Next, I'm going to add in iron 3. Okay, so this iron 3. Okay, some iron 3 over here. And to add in a little bit of iron 3. Okay, yep. Okay, so same idea. Sodium hydroxide, first one. Okay, I think you roughly know what you expect to observe. Reddish brown PPT. So very clear cut. Okay, iron 3. Okay, reddish brown PPT. Okay, so it's a very clear cut reddish brown. It's more reddish brown. Some of you describe it as brown, but it's it has the kind of rust color. Okay, so red brown. Okay, might be a better description. Okay, going to add in aqueous ammonia. Okay. Okay, so you can see that the PBT is being formed as well. Okay. Earlier on for sodium hydroxide, I forgot to add in excess aqueous ammonia to just check for its solubility. Okay, so I'm just going to add in, excess sodium hydroxide earlier on. So I added in excess aqueous ammonia. Okay, so this is what you will expect to observe. Okay, so I'm going to add in excess sodium hydroxide just for completion. Okay, I'm going to swirl a little bit. Okay, so this is the one using sodium hydroxide. This is the one I've added using aqueous ammonia. Okay, you can tell the difference or not. Quite similar. Okay, so insoluble in excess. I'm going to put it down. Later, it should settle down. Okay, I'm going to revisit iron 2. Okay, so I'm just going to look them up. My left hand, the one with excess hydroxide, right hand, aqueous ammonia. Okay, can you see the difference? Okay, there's a slight difference. You'll notice that if I add in aqueous ammonia, right, the PBT gets oxidized faster. Yeah, correct. You can see that the reddish brown here is much more apparent as compared to the one I've added sodium hydroxide. Okay, can you see the PBT settling down? Maybe not really, but I'm just going to leave it there for a while more. Okay, let's check out the one I've added aqueous ammonia and sodium hydroxide. Okay. Can you see that the PBT starts to settle down? Okay, yep. Okay, right now I'm going to move on to the next one, which is extremely familiar to everyone, and we really love the color. That is copper 2, right? Okay, so I mean, you don't even need to do anything, you know what color you get ready, but nonetheless, let's try because we really love the color of the complex, right? Okay, yep. Okay, so the first thing I'm going to do is sodium hydroxide. Okay, dropwise. Okay, so again, you probably know that the blue PBT is not going to be soluble, but nonetheless, let's try and observe it. Okay. Okay, in excess. Okay, you can see that the solution. Okay, you get a very nice blue PBT. Okay, insoluble in excess. Okay, right. We're going to add in a bit more, just to satisfy your curiosity. Okay, and then I'm going to do more swirling. Okay. Yep. Okay, so this is the blue PBT, which you will observe. Okay, the typical blue PBT you observe when you add sodium hydroxide. Okay, yep. Next, aqueous ammonia. Okay, aqueous ammonia is all-time favorites. It's my favorite anyway. Okay, so please watch without swirling, and with swirling, you will also see the tetraamine copper, observe the tetraamine copper 2 complex being formed without swirling. Okay, just at the surface. Can you see that the surface has a darker shade? Very clear-cut darker shade, right? Yeah, it's very clear-cut because that is the tetraamine copper 2 complex on the surface, and then the white PBT, the blue PBT slightly above over here and slightly below, okay, is the copper 2 hydroxide. If I swirl it, the solution now experience the volume. Okay, so now of the solution. So now you're going to get the characteristic blue PBT. Okay, now I'm going to add in more excess. Okay, can you see that the PBT starts to dissolve to give you a dark blue solution? Okay, so this is not dark blue enough. Why? Yeah, because again, I have not added in a lot of excess aqueous ammonia. Okay, I'm going to add a lot in excess so you can observe the dark blue solution. Okay, that should be sufficient. Okay, so please observe the dark blue complex. Okay, so this is the dark blue solution, which is the tetraamine copper 2 complex. which you can easily explain using the same sets of equations. You just need to change the species from zinc to copper. Okay, what about getting a little bit more innovative? Add a little bit of sodium hydroxide. Sorry, a little bit of hydrochloric acid. Okay, same thing. You're going to observe the PPT form, and then after that, swirl it. It may disappear because too much equals ammonia, but just add a bit more, and then you start to see the whole solution mess up with a little bit of white, a little bit of blue PPT, and then some dark blue complex. This is clearly a solution. You can sort of see through it. I mean, I won't say you see through it, but yeah, you can see that it's a solution. Okay, unlike what you have earlier on, this is not a solution. Okay, can you see that it's opaque? Okay, in case you're wondering what this is the one with excess ammonia into iron 2. Okay, you can see through it. Okay, so this is quite clear cut as a solution. Okay, I'm going to add in dilute hydrochloric acid. Okay, dropwise, you see the PPT now being formed at the site. Okay, you see the PPT now slowly but surely being formed, floating around, don't know where to go. Okay, a little bit more. Can you see on the surface? It's already the PPT form. Okay, and then going to swirl it a little bit. Okay, can you start to see at the bottom of the test tube? Now that's the copper 2 hydroxide. Okay, so even if I swirl it continuously, you can see the solution become a little bit more opaque. Okay, now I'm going to add more. Okay, so clearly now it's a mess already. Okay, if I don't swirl it, it's a mess. If I swirl it, I'm going to get the pale blue PPT, largely the pale blue PPT. Okay, you can still see some of the hexyl amine copper 2 complex, just a little bit, but yeah. Okay, and then when in excess of hydrochloric acid, I'm going to observe the pale blue solution, which is expected of copper 2. Okay, just going to swirl very, very slowly. Okay, I need a glass rod. Okay, other than that, if I just continue swirling, it should be okay. Okay, you can see that the stubborn PPT right at the bottom is floating up. Okay, and then it's dissolving, right? Okay, so that's it. Okay, you can see it. Test tube feels warm. Okay, yeah. So this is what happened when you add in dilute hydrochloric acid dropwise and then in excess, and then you're going to see the reappearance of the pale blue PPT, and then after that in excess to give you back the pale blue hexyl aqueous copper 2 complex. Okay, now this is the pale blue PPT. I'm going to swirl it a little bit. Okay, you get when you add in sodium hydroxide. Okay, so this is the pale blue PPT. You can see that maybe there might be some contamination because the color is not exactly homogeneous or different forms of the copper 2 hydroxide PPT. Okay, and then this is the reddish-brown PPT earlier on. Can you see that it's settled down already? Okay. This is the green PPT. It's more or less settling down. Okay, can you see the surface over here? Yeah, so settling down, so it's not transparent. You can't see through it. Okay, right. Okay, so now we have done quite a bit already. So we have almost done with all. We are left with chromium 3 and manganese 2. Okay, so just going to perform manganese 2. I think manganese 2 is not something which you are familiar with. Okay, so just going to take out the solution. So this is the manganese 2 sulfate. Okay, over here it appears a little bit pink. Okay, but you can't really observe it to be pink. Okay, I'm going to add using a test tube. Okay, so again, 1 cm depth, 1 cm depth. Okay, many students confuse manganese 2 with the other color solution like aluminum 3, zinc 2, and magnesium 2, because they fail to observe that when you add in sodium hydroxide or aqueous ammonia, although you get white PPT. Actually, the PPT is not exactly white. We describe it over here in the QA notes, right? As off-white. So it has a bit of brown shades, and then it will be rapidly oxidized in air to give you a brown PPT. Okay, so let's prove it. Okay, sodium hydroxide. Okay, we try to observe. Add in. Okay, so you can see the PPT. Can you see that it turns brown quite quickly? So this is more off-white, right? It's not really white in color. Then can you see that the surface, the PPT, rapidly turns brown? If I swirl more, it turns brown rapidly in air. Okay, so this is a characteristic of manganese 2+. Okay, when manganese hydroxide is being formed, it will rapidly oxidize in air to give us manganese 3 hydroxide. Okay, so if I add in excess, you can see that the solution is clearly filled with brown PPT. Okay, yep. Okay, next, similarly, aqueous ammonia. So please observe very carefully. Okay, off-white PPT form, and then rapidly turns brown in contact with air. Okay, so I'm not sure whether it's obvious to you, but just wait. Okay, so the solution is a bit brown, milky. Okay. Yep, I'm going to add in excess. Equals ammonia. Okay, so I'm going to swirl it continuously. Okay, see it's brown in color. Okay, so you'll record the observation as off-white PPT observed. Okay, and then rapidly turns brown when in contact with air. Okay, yeah. So the final two we are looking at will be chromium 3 and ammonium. I think ammonium is very classic. Okay, most of you should know how it looks like, or I mean it's colorless, but you know what to test for. Yep. Okay, so we'll move on to chromium 3 next. Okay, we'll now be looking at chromium 3 chlorides. Okay, so the chromium 3+ complex, which you're going to observe later. So I think chromium 3 is something which most of you have not observed it. So do pay attention to what you expect to observe. So again, I'm going to add 1 cm depth. Okay, so chromium 3 is actually green in color. Okay, so this is the chromium 3 solution. Okay, yep. So again, let's observe what happens when sodium hydroxide is being added. Okay, so please observe. Then you'll be able to tell what's the difference between the color of the PPT with that of iron 2. Okay, so you can see that there's a slight difference in the color, and I think slight difference, quite similar, I mean to some extent, but it doesn't turn brown when you leave it in the air for some time. Okay, so we can continue to observe it. Okay, I'm just going to swirl it. Okay, a little bit more, and then now I'm going to add in excess. Okay, to see whether you get a dark green solution. Okay, so this is the dark green solution which you are expecting when you add excess chromium, add excess OH minus to chromium 3 hydroxide. Okay, so this is the solution. Okay, maybe it's a little bit, I think you can't really see so well in the video. Okay, okay. I'm just going to add a bit more sodium hydroxide to make it a little dilute so that you can see it clearly. Okay, so this is the dark green solution we're talking about. Okay, when you add excess OH minus to chromium 3 hydroxide PBT. Okay, yep. Then what about aqueous ammonia? So again, this is the chromium 3. So we're going to add aqueous ammonia. So same thing, going to get a gray-green PBT. Very, very similar to iron 3, but you notice that at the side of the wall, right? It's a bit grayish in color, right? But it doesn't turn brown when you expose it to the air. Okay. So I'm just going to continue to swirl it. Okay, then after that, I'm going to add excess ammonia. Okay, you notice that it's a bit like chalky green. Okay, but in most cases, it's often described as gray-green. Okay, see, you can observe that it is not soluble in excess ammonia. Okay, yeah, compared to the solution, compared to sodium hydroxide. Okay, so just going to put the two side by side. Okay, one is gray-green, the other one is a dark green solution. Okay. Okay, yeah, so that's all for chromium 3. I mean, not very inspiring, not very different. Most of you have not done it before, but yeah, so this is the appearance if you really need a reference point. Okay, I think on the screen it might not be very clear that it's gray-green. My apologies, I'm not sure how I can make it like even more gray-green. Like I think just take a photo or something, but yeah. Okay, so yeah, it's a bit gray-green. Okay, at least that's what appears to me, but maybe not on your end. Okay, because I can look at the screen right now because when I'm recording, I can see myself. So I know that you probably don't observe it as very gray-green. Yeah. Okay, but maybe when I put it side by side as a contrast, you can tell. Okay, yeah. Then the final one, not exactly the final one, will be ammonium cation. Okay, so ammonium cation, you know that I'm not going to add aqueous ammonia to it because it just doesn't make sense. Okay, but I'm just going to add in a little bit of sodium hydroxide and then observe what's going to happen when I warm up the solution slightly. Okay, right now I'm going to add ammonium sulfate, okay, to give me the ammonium cation. Okay, once you're done, I'm going to prepare my moist red litmus. Okay, just going to prepare it in advance. Just take a little bit of deionized water, just moist it for a while. Okay, and then I'm going to put it near the test tube rack so that if I need it, I can take it. Okay. Right. First, I think I switch on the thing first. Okay. Going to add in sodium hydroxide. Okay. Dropwise. Okay, so how much change? Okay, so no visible change. Okay, this is the litmus. You can see that it's red in color. Okay, now this is a technique which you might want to follow. Just heat up a little bit to release some of the ammonia. And then slowly test. Okay. You observe that moist red litmus turns blue. Okay, so just a bit. Okay, I'm going to heat up more. Okay, I think it's quite obvious. Moist, red litmus turns blue. Okay, going to switch off the flame now. Okay, after you switch off the flame, you can actually continue to just put it near the mouth of test tube. Okay, because more and more of the ammonia will be given out, and then you will notice that the red litmus continues to turn blue. Okay, because you need a bit of time for the ammonia to be evolved. Okay, yeah, so this is a technique which you can follow. Remember not to touch the litmus on the mouth of test tube. Okay, just put it at the mouth. Don't touch the test tube. Okay, yep, I think this is clear cut. Okay, so that's for the test for ammonia. All right, we are now left with barium and calcium. Not very inspiring because according to the data booklet, you're not going to expect any precipitates to be formed when you introduce sodium hydroxide and aqueous ammonia. But nonetheless, we'll go ahead with our testing. Okay, so I'm just going to add 1 cm depth of the reagents. This will be calcium 2. Okay, so in both test tubes. Okay, so I'm going to add in sodium hydroxide dropwise. Please observe whether you observe precipitate being produced. Okay, so you can see that the solution remains colorless. Okay, you do get a little bit of turbidity. Okay, because if the concentration of calcium is relatively high, yeah, so this is expected as well, was shown in the data booklets. Okay, so when you introduce aqueous sodium hydroxide in, you should expect a little bit of turbidity or white PVT when the concentration of calcium 2 is high. Okay, so this is expected. Okay, so let's try for aqueous ammonia. Okay, so I'm just going to add it in. Okay, so for aqueous ammonia, you observe that solution remain colorless. Okay, so again, this is expected as well. Okay, so no tricks, right? So it's very clear over here. Okay, next, we're going to do for barium. So this is the freshly prepared barium from barium nitrate solids. Okay, so again, I'm going to add 1 cm depth. Okay. Okay, then I'm going to add sodium hydroxide dropwise. Okay, so please watch. Color solution, add it dropwise. Okay, solution remains colorless. Okay, so this is expected. Okay, so if the solution is not pure, you would expect some precipitates. Okay, so it could be perhaps due to the presence of other contaminants, cations. Okay, so it's colorless. Okay, so that's fine. For aqueous ammonia, okay, so we'll try the same thing. Okay, so add dropwise. Okay, so you notice that solution remains colorless. Okay, all right. Yep. So that's it for the cations series. We'll move on to look at the anions and to test for gases next. Okay, so welcome to the beginning of the anion series. First, we'll be testing for the presence of carbonates. Okay, so you were told from the QA booklets that if carbonate is present, when you introduce dilute acid, CO2 will be evolved. Yeah, so we can do this together with the testing for carbon dioxide gas. Okay, so before that, I'm going to prepare some lime water. Okay, so it's prepared already. So this is freshly prepared lime water. I'm just going to introduce it into a test tube. Okay, just make sure the test tube is dry. Okay, so I'm going to introduce some lime water in. So this is lime water delivery tube. I'm just put it in first. Okay, and then I'm going to take a clean and dry test tube. With that, I'm going to introduce some hydrochloric acid. Okay, so very carefully, I'm just going to introduce it over here. Okay, and then I'm going to take some sodium carbonate. I'm going to introduce it at the wall of a container so that later on I will put the delivery tube. I will just cap it And then slowly I will tip the sodium carbonate in so that the reaction, or so that I will be able to capture most of the CO2 evolved. Okay, so I'm just going to do it really, really carefully. Yep, so this is the best method to achieve the best results. Okay, so I'm just going to be really careful here. Okay, yep, so you need to have a bit of green fingers. Okay, yep, and then so please observe. You see the production of the white PPT. Okay, yeah. So I'm going to swirl more. If I'm introducing more CO2, you'll notice that the white PPT slowly dissolve. Okay, and you get a colorless solution. Okay, do you observe that? Okay, so initially, when CO2 is being introduced and is passed through the delivery tube, you observe white PPT. Okay, and then after that, when excess CO2 is being introduced, the white PPT dissolves to give you a colorless solution. Okay, why is that the case? That has been covered, I think it's in practical 15, but nonetheless, we're going to use today's, we're going to use this opportunity, right, to explain to you again why that is the case. Okay, so I'm going to use the board similar to previous experiment. Okay, so first of all, right, we need to introduce what exactly is lime water. Okay, we need to know its content. So lime water essentially is calcium hydroxide. Okay, yeah. Then next, what exactly is happening when we introduce CO2 into the solution containing lime water? When we bubble the effervescence, the colorless odorless gas into lime water, what exactly is happening? Okay, so you are aware that CO2 looks like this linear molecule. So I'm going to just incorporate a little bit of organic chemistry ideas in. Not really organic chemistry, but it's more of elocution, so that you can integrate between what you have learned in organic chem and inorganic chem. Okay, so CO2 is like a dicarbonyl with an electron deficient carbon center. So when I introduce CO2 into the system, the OH minus present in the system will perform a nucleophilic attack on the carbon dioxide. And in the process, it's able to produce the bicarbonate. Okay, so this is the bicarbonate being produced. Okay, HCO3 minus, or we call it hydrogen carbonate. Okay, and of course, there's a protonic hydrogen over here. Okay, and the OH minus present will further deprotonate this. Okay, and then I'm going to end up with carbonates. Okay, so this is the carbonate which you are familiar with. And this carbonate, based on what we have learned regarding insoluble carbonate or regarding solubility product, we know that calcium 2 plus and carbonate will undergo precipitation to give us calcium carbonate, which is a solid. So that's the white PPT you observe. Okay, yeah, but when the white PPT is being produced over and over, and when most of the calcium 2 has been precipitated out, you will notice that a small amount of Ca2 plus and carbonate is being maintained by virtue of its KSP. Okay, so that will be the second equilibrium which you learn under solubility product. So I repeat, a small amount of calcium carbonate, or rather a small amount of calcium 2 plus and carbonate ions are maintained by virtue of the KSP. So this is the white PPT. I'm maintaining a small amount of these two in the system. But if I keep bubbling CO2 in, there's no more OH minus or not enough OH minus to react to give me carbonate. Then what is going to happen? Okay, so what is likely to happen will be, I'm expecting the presence of carbonic acid to be formed instantaneously. Okay, so in that sense, the carbonic acid that is formed when you bubble CO2 in, right, is likely to react with the carbonate present, and in the process produces hydrogen carbonate. Okay, so it produces this hydrogen carbonate. Now, what's going to happen is that this carbonate is being taken from the small amount of carbonate being maintained by virtue of the KSP of calcium carbonate. Yeah. So when the carbonate is being consumed, the position of equilibrium of two will shift to the right. And this leads to the dissolution of calcium carbonate. And when calcium carbonate dissolves, once again, you see the solution as colorless. Okay, because calcium hydrogen carbonate is soluble. Okay, and that is exactly what you observe over here, or rather what you observe over here. Yeah, so it's a colorless solution. So nothing has changed drastically. Okay, right. Okay, so that will be the end of the demonstration for the production of CO2. Okay, so next we are going to move on to testing the halides. Okay, we're going to go in order. So we have chloride, bromide, and iodide. I'm just going to introduce them into the test tubes. Okay, just a little bit of the solution. Maybe half a cm depth. Okay, so I'm just going to put them side by side so that it's a good contrast for you. Okay, so on the left, I have chloride. In the middle, bromide. Okay, and then on the extreme, on my extreme right is iodide. Okay. Okay, so similar heights. We're going to introduce silver nitrate dropwise. Okay, so please observe. Okay, you can see the white PPT appearing. So this PPT is very white. Okay, in the middle, you can see the PPT is slightly different in color. We describe this as cream. Okay, there's a slight yellowish hue. Okay, and then the one on my extreme right, it's a yellow PPT appearing. Okay, you can see that it's clearly yellow. So have them at a similar level. You can see that maybe the level is not quite similar. I'm going to add a bit more in the middle. Okay, and then a little bit more on the left. Okay. Yep. Okay. I'm going to use a filter paper so that you can see the contrast. Okay, it goes from white to cream to yellow. Okay, then right now I'm going to add in aqueous ammonia to test for their solubility. I'm going to add to the same height. Okay, so the one on the left with the bromide, you can see that it clearly dissolves. Okay, so it's quite clear cut. There's still some stubborn PPT around, but we can let us try to dissolve it later using a stirring. I mean, using a glass rods. Okay, I'm going to add into the middle. Okay, the cream PPT. You can observe that partially soluble, but still the bulk of it is still lying at the bottom. Okay, the yellow PPT insoluble in ammonia. Okay. Okay, I think it's quite clear cut now. Okay, so I'm just going to use a glass rod to try to dissolve the one in the middle. I mean at the sides. Okay, I'm just going to break up the particles. Okay, and then I'm going to swirl a little bit more. Okay, of course, add more aqueous ammonia. We'll do the trick. Okay, and then I'm going to swirl more. Okay, you can see that the white PPT now dissolves. The yellow PPT remains largely around present. The cream PPT in the middle, you can observe that it partially dissolves. Okay, when we add in a lot more ammonia. Okay, so we have the three solutions here side by side for you as a comparison. Okay, so the one on the left, white PPT dissolved in excess ammonia to give us a color solution. The one in the middle, cream PPT partially dissolved in aqueous ammonia. For silver iodide, the yellow PPT remain insoluble in excess ammonia. Okay, right. You can still see some stubborn particles, silver chloride, because they clutter together. But if you swirl more, you can observe their clear solubility, clear dissolution. I mean. Okay. Yeah. Okay. So with that, we have tested for chloride, bromide, and iodide. Okay, so next we are going to test for nitrates, and from our QA notes, you know that test for nitrate involve the reduction of nitrate all the way to ammonia. So we need to prepare moist red litmus. So let me just take a red litmus paper. Okay, going to moist it a little bit with deionized water. Okay. Yep, and then just going to place it at the sides, and then with a clean and dry test tube, I'm going to introduce some barium nitrates. Okay, and then I'm going to introduce sodium hydroxide to the solution. Okay, and then some aluminum powder. Okay, to perform the reduction. Okay. Okay, I'm going to heat up a little bit because a little bit of activation barrier is needed to kickstart the reaction. This is the moist red litmus. Test. Okay. Okay, check out if the moist red litmus turns blue. Okay, slowly but surely. You just need a little bit more ammonia to be evolved. Okay, I think you can observe that it's quite obvious. All right. Okay. Yep. I'm going to stop. Okay. Unfortunately, we cannot test for nitrites because nitrite is explosive. So by Singapore's law right now, it's difficult to purchase nitrite, or it's not very easy to get hold of nitrite because of the fact that they try to prevent unauthorized usage. Yeah, so we can't do the nitrite anion test over here for demonstration purposes.
I've managed to find a video on YouTube to demonstrate the test for nitrites, and I've incorporated it into this video to complete the discussion. So over here we have solid sodium nitrite, and it's being introduced into a clean and dry test tube. This is followed by introducing dilute hydrochloric acid, which will protonate nitrites. Upon protonation, nitrous acid will be produced. However, nitrous acid is not stable and it will immediately decompose to give us nitrogen monoxide. Nitrogen monoxide is not stable as well, and it will immediately be oxidized by air to give us brown nitrogen dioxide, and you can observe it by the brown color. You can test for the presence of nitrogen dioxide by placing a moist blue litmus near the mouth of a test tube, and it will turn it red. Over here we have a confirmatory test, so we have added some solids sodium nitrite in, and this is followed by adding distilled water. You will notice that upon adding some sulfuric acid, some brown fumes will linger above it, and I think you should be able to guess that it is nitrogen dioxide. And now when we introduce potassium permanganate in, you will notice that the purple potassium permanganate decolorizes. This is due to the fact that nitrite is being oxidized to nitrates, and at the same time permanganate is being reduced to colorless Mn2+, as demonstrated by the equation given there. Okay, so next we'll move on to the next section.
Okay, next we are going to test for the difference between sulfates and sulfites. So we have zinc sulfate over here, which give us sulfates. Okay, so 1 cm depth. I'm going to add in barium nitrates. Okay, so dropwise, you're going to see a white PBT appearing. Okay. Yep, we're going to add excess hydrochloric acid to see whether the PBT dissolves. Okay, so clearly it remains insoluble. Okay. Yep. Then next I'm going to do the same thing, but before that, I have some sodium sulfite. Okay, going to add in some water to dissolve it. Okay. Sodium sulfite needs to be prepared fresh, so that explains why I'm only dissolving it right now. Okay, so just going to just swirl it a little bit. Okay, so this is freshly prepared sodium sulfite. Okay, I'm going to introduce into the test tubes. Okay, 1 cm depth. Barium nitrates, I'm going to add dropwise. So again, what PBT observe. Okay, so barium sulfide is also insoluble in water. Okay, so shouldn't come as a surprise. But if I add excess hydrochloric acid, please observe. Okay. You observe that the PBT actually dissolves, okay, quite readily. Okay, but do take note that it needs to be prepared fresh so that the dissolution is quite obvious. Because sulfite gets oxidized to sulfate quite quickly. Okay, if I use another clean test tube, I think you should be able to observe it. I'm just going to pour it out. Some of the white PBT. And then I'm just going to add in excess hydrochloric acids. You can see that the dissolution should be quite straightforward. Okay, you can still observe a little bit of turbidity. I think there's no choice. Okay, but yeah. How can we understand this? Okay, how can we understand why is it that when we add in excess acid, then we observe the PBT dissolved? Okay, I think I've explained that before, but I'm going to explain it again on the board. Okay, but before that, let me just erase this portion. Okay, so we know that barium 2+ and sulfite together, you can precipitate out barium sulfite as a solid precipitate. Okay, right? And then when almost all the barium sulfite has been precipitated out, then the little bit amount of barium sulfite precipitate will be able to maintain a small amount of barium 2+ and sulfite by virtue of its KSP. Okay, so we understand this as well. What happens when we add in HCl or when we acidify the solution? Okay, so we need to be aware of what exactly is happening when acidification takes place. Okay, so first of all, we need to understand that sulfurous acid, which is H2SO3, is a weak acid. So it prefers to exist in a molecular form. So we have equation 1, equation 2. Okay, so it will be helpful if you can write equation 3 in the form of the hydrogen sulfide, which is the acid of, or rather you can call it the conjugate acid of sulfide. Okay, so HSO3 minus equilibrate to give us SO3 2 minus equals plus H plus. Okay, and then at the same time, we have H2SO3 equals equilibrate to give us HSO3 minus equals plus H plus. Okay, so in the presence of excess acid, I expect the position of equilibrium of 3 to shift to the left, equilibrium position of for the shift to the left. Okay, this is due to the consumption of sulfite. And when that happens, it disturbs the solubility equilibrium of barium sulfite. And because of that, barium sulfite dissolves to give us a color solution. Yeah, and in most cases, like what we have observed earlier on, you don't really see the barium sulfite dissolving completely. Okay, I think yeah, I have one over here, is quite complete. Just trying to observe. Yeah, so it's quite complete. A little bit of turbidity, but yeah, the oxidation of sulfite it happens relatively quickly. So it's kind of like no choice. Okay, so I hope you can understand the chemistry I've put on the board. Okay, so in your data booklet, it's written that the white PPT produced with barium soluble in dilute strong acid, and then SO2 is also liberated with dilute acid. Okay, so we're going to do this test for sulfite, which leads to the production of SO2. And you notice that this is also one of the tests you need to know how to test. This is also one of the gas you need to know how to test. And that's the production of sulfur dioxide, which turns acidified KML4 from purple to colors. Okay, we can easily do that using filter paper. Okay, so I'm just going to cut it in such a way that I'm going to get a small strip, and then from there I will be able to test for the production of SO2. Okay, I think the production of SO2 has also been done in one of the videos I produced earlier on, but it's okay. We can always do it again, just for you to take note of it. Okay, so right now in a clean test tube, I'm going to take a clean test tube. Okay, I'm going to introduce some sulfites. Okay, where's the sulfite? Some sulfites, which, yeah, this is the sulfite we have. Okay, just introduce a little bit of sulfites. Okay, I'm just going to put in a little bit of hydrochloric acid. Okay, so you can be sure that H2SO3 has already been produced. Okay, later on we're going to do some heating. Okay, so the little bit of makeshift KMNO4 paper I've produced, the filter paper, I'm going to just put the KMNO4 in. Okay, so this is the KMNO4. I'm going to turn on the flame. Okay, please observe it. Okay. Okay, just going to shift it nearer to the camera. Okay, is it going to decolorize? Okay, can see that it turns brown a little bit. Okay, shift it more. Okay, I think it's quite obvious. Okay. I think decolorize quite a bit already. Okay. Right. Okay, let's try a little bit more. Okay, I think the filter paper more or less decolorized almost completely. Okay. Okay, just introduce more. Okay, so this is the test for SO2, which is a reducing gas. Okay, so SO2 will be able to reduce KMNO4 to the colorless Mn2+. Okay, so right now we are left with chlorine gas, which we have not tested. Let's do the chlorine first. So this is sodium chlorate. I'm going to just add in a little bit of acid, okay, to acidify it. Okay, so it will lead to the production of chlorine, but before that, let me prepare a damped blue litmus. Okay, prepare the damped blue litmus. Okay, just going to prepare it. Okay. Going to add in a little bit of sodium chloride. Okay. Just add in some acids. Okay, see that. That's going to observe the chlorine gas. Being produced. Okay. You can see that the litmus turns red and then it gets bleaches. Okay, can you observe that? It's being bleached. Okay, this is quite obvious. Okay, bleaches means it turns white. Okay, if this is not convincing enough, okay, I can maybe introduce a little bit more acids. And then maybe a little bit more sodium chloride. Okay, let's take a look. Okay, so damped blue litmus turns red and then it gets bleaches. Okay, so this bleaching is quite obvious. It turns into a white paper. Okay, yep. Okay, next we are going to test for hydrogen gas. Okay, so I'm just going to take a test tube and introduce some hydrochloric acids. Okay, so just a little bit of hydrochloric acid will do. And then I'm going to introduce some zinc granules. Okay, so just 4 will do. Okay, you will notice that there's a little bit of effervescence being produced, but this is definitely not enough. Okay, so what I'm going to do is I'm just going to heat up slightly, just to give it enough activation energy. Okay, just very slight heating to accelerate the reaction a little bit. Okay, so I think I have enough so that it's not too hot. I can hold it with my bare hands. Okay, can you observe the effervescence? Okay, yep. So I'm going to collect a lot of gases and then I'm going to test it with a burning splint. Okay. Okay, I'm going to collect a lot of gases right here. Okay. See, I'm holding it. I'm going to test it with a burning splint. Okay. Let's try it. Okay, you heard that? Okay, it extinguishes the burning splint with a pop sound. Okay, so let's try again. Okay, you heard that? Yeah. Okay, so the net result you observe is the production of hydrogen, okay, will extinguish a burning splint with a pop sound. Okay, you heard that, the slight explosion. Okay, but it's not really an explosion, just a pop sound. Okay, yeah. And you can see that the reaction is continuing. Okay, the effervescence given off continues. Okay, yeah. All right, so next we are going to move on to test for oxygen gas. Okay, yeah. So for oxygen gas, it's different from hydrogen. Usually students get confused. For oxygen gas, it is a lighted splint. Okay, it is different. Okay, it's not a burning splint. or we also call it a glowing splint. Okay, yeah. So we're going to do that. We're going to do that by introducing H2O2. Okay, so let me get some H2O2 over here. So this is hydrogen peroxide. Okay, we need this. We also need a little bit of oxidizing agents. Okay, so let me find an oxidizing agent. Potassium permanganate, perhaps. Yep, it's potassium permanganate. Okay, so I'm just going to get ready. Okay, I'm going to introduce some H2O2 over here. Okay, peroxide. Let's introduce it. Okay, and then I'm going to introduce potassium permanganate. Okay, you can observe the production of oxygen gas. Okay, I'm going to test it. Okay, so this is a lighted splint. Observe. It glows again, right? Okay, so let's try again. Okay. All right. Okay, so this is the test for oxygen. Okay, so it reignites a glowing splint. Okay, so we can continue if you want to. Okay, because it's still glowing. How do you know you're ready to test? When you feel the pressure of the oxygen trying to force its way out. Okay, then you put it near. Okay, yeah. All right, so I hope you are clear how all these gases are being tested, especially for hydrogen and oxygen, because most of the time student tends to get these two mixed up or use the wrong test. Okay, but we also need to be a little bit careful regarding the production of oxygen. The reason being, sometimes there are certain reactions, for example, in the decomposition of solid aluminum nitrate, which I did demonstrated in one of the earlier videos, right? It's very difficult to observe the glowing, the reignition of the glowing splints. The reason being the decomposition, what is accompanied in the decomposition, right, consists of water vapor and steam as well. So it will kind of like, cause your wood to wet out a little bit, so it's difficult to observe that glowing splints reigniting. All right, finally, we are at the last part, section 9D on the colors of halogens. Yeah, so I just want to perform a demonstration so that you get to observe the various colors. Okay, so first I will have a test tube over here. I'm going to introduce some NaClO to generate chlorine. Okay, I need to introduce a little bit of acids for chlorine to be generated. Okay, I'm just going to show it. Okay, just going to take a filter paper so that you can observe that the solution is pale yellow in color. Okay, maybe I can introduce a little bit more acids. And perhaps just a little bit more. Yeah. So the pale yellow is not very visible over here. Okay, but nonetheless, I hope you can get to observe it bit by bit. Okay, then I'm going to introduce hexane. Okay, this is hexane. Okay, I want you to observe the color. Okay, an organic layer. Hexane is less dense than water, so it will float on top, and they don't mix well. Okay, so I'm just introduce a little bit of hexane in. Yep. just a little bit. I'm going to swirl continuously. Okay, yeah, I just want you to observe the top layer. Do you observe it as yellow? Okay, yeah. Chlorine is more soluble in hexane than water, as all of you know, because chlorine is able to form favorable dispersion forces with the hexane non-polar molecules. Yeah. So you can see observe the greater solubility of chlorine in hexane. Okay, so I think that explains what's been written on your QA notes. So the color of chlorine in hexane and water is both pale yellow. Okay, next I'm going to demonstrate for aqueous bromine. Okay, so for aqueous bromine, I'm going to use another test tube. I'm just going to introduce some bromine in. Okay, yep. So bromine within our, I'm just going to dilute it a little bit. Okay. Okay, so within our curriculum, we describe the color of bromine in water as orange. Okay, or you can describe it as pale orange. Okay, now observe what happens when I add hexane. So again, hexane will float on top of the aqueous layer. Okay, I'm just going to swirl more. Okay, what do you notice? You notice that bromine dissolves favorably in hexane, and what you observe here is an orange-red solution. Okay, yeah, so that explains why there's a difference in the way we describe the color, right? So in aqueous solution, bromine is orange. What you observe earlier on, if you need to, just rewind the video. Then now you observe it as orange-red. Okay, so I hope you get to see the difference. I mean that's the whole point of this video. It's really for you for you to observe the color and to remember it so that you form an impression. Okay, finally, we are looking at iodine. Okay, so I have iodine solution here. Just going to introduce. Okay, so this is quite concentrated. Okay, so I'm going to dilute it with water. Just a little bit of water. Okay, so iodine by and large, you describe the color as brown. Okay, of course, if I dilute it a lot, it will be yellow. Okay, but by and large, we describe this color as brown. Okay, not reddish brown. It's a bit different. There's a difference in the color. Okay, this is orange straight. Okay, so yeah. So just make sure that you observe it carefully. Okay, so now interesting. I'm going to add hexane, right? Watch what happens. Okay, I'm going to swirl it. You observe a purple layer on top. Yeah, so the color of iodine in hexane is purple. I'm going to introduce more hexane. Okay, I'm going to swirl more. You will also see that the aqueous iodine solution, the aqueous iodine layer actually clears up. Okay, and it becomes a little bit more yellowish. Okay, yeah, so yeah. Okay, can you observe that iodine is purple in hexane? Okay, yeah. So I hope through the demonstration, it will help you, it will impress upon you that this color written here is real. It's not like we make up the color, not like the chemists make up the color. Okay, so this is really what you observe. Okay, so I'm just going to put them side by side so that you get to see the different colors. Okay, so going from left to right, okay, we have chlorine, yellow in the organic layer, pale yellow in aqueous solution. Then we have bromine, orange straight in the organic layer, orange, okay, in the aqueous solution. Then we have iodine, purple in the organic layer, and then brown in the aqueous solution. Of course, now it's not so obvious because some of the chlorine, bromine, iodine, or the bulk of it has already dissolved in the organic layer, so you don't really get to see the obvious colors difference. Okay, so with that, I hope you find this particular video useful for your learning, because essentially we have gone through the whole set of section 9 of your data booklets to show you the various appearance of the PPT, the complex, how to test for the gases, how to test for the anions, as well as section 9D, the various colors of the halogens in organic and aqueous solution. Okay, so with that, all the best for your revision, and we get to see you in the next video.